15 hours, right?
Yeah, definitely. Yeah.
Yeah.
So you had your tea or coffee, something early in the morning, or?
Oh, actually, that's a very good idea. Let me go back to put some coffee in my mug. It's already prepared.
You have
So,
1 minute. If you want to take 1 minute, it is okay.
all right, just 30 seconds.
Yeah.
Okay. Now I think it's meeting
nice.
recorded. Okay, cool. So you thought that my last name was Carlos and my first name was Juan.
Very, very sorry. And I think Indranil just corrected me. It's Juan. I should pronounce. I always say you Juan, but yeah, the correct is Juan, I guess.
Oh, okay. That's another point. Well, that's the same in, I think, yeah, most of the people pronounce like that, but well.
Okay. So if one pronounce your full name, it is Juan Rodriguez Ramirez, and the Carlos comes somewhere, or?
No. Juan Carlos is my name.
Okay, that's the first
Rodriguez Ramirez is my last name. The thing is that here in Mexico we have two last name, and I think in most countries in Latin America we have two last name. But the thing is that this is a very common last name. That's why I put them together as if it were only a single word.
Okay. Yeah. Yes. Yeah. So yeah, now I understand it. So I put Juan Carlos. Yeah, understanding it is the full name.
Yeah. No. But
okay. So we can wait maybe 1 or 2 minutes if more people.
Yes,
join,
of course.
then we can start.
Yeah. So, what is your current project about over there in is that correct? The institute, Aryabhata Research Institute? Yes, right?
Yes. It is correct.
Okay. So, what are you working on currently over there?
Something about pulsar wind nebula.
Pulsar wind nebula. Oh, cool.
Yes.
But individual sources or population as you commented previously?
For example, for now, it is just the lasso sources, individual sources, few of them. But yeah, working something like, ultra high energy, gamma rays.
So I suppose that you are modeling non-thermal emission or
yes,
some observation.
Yes.
Oh, cool.
Okay, so maybe I think I can just introduce you and then we can start.
Oh, cool. Yes.
So good afternoon, everyone. And so for today's seminar, we have Juan Carlos Rodriguez Ramirez, and he will speak about something about blazars and modeling, like multi-messenger connection, electromagnetic radiation coming from blazars, and then how neutrino potential neutrino sources can be useful to understand the jet composition. So Juan did his PhD in 2017 in Institute of Nuclear Sciences in UNAM, Mexico, and he worked basically on gravitational and radiative force balance in molecular hydrogen regions that helps in understanding the star formation and kind of processes. After completing his PhD, he moved to Institute of Astronomy, Geophysics, and Atmospheric Sciences in Sao Paulo, Brazil. There he is exploring multi-messenger connection, and today he is going to talk something about that, how we can study the blazar jets relativistic outflow, and how magnetic reconnection and neutrino connection helps us to understand these jets. So Juan, please, you can start now.
Oh, thank you for the introduction, and also thank you for the invitation to give a seminar in your institution. I'm very happy to share with you some of my current results. As a matter of fact, I will share with you some ongoing results in the very recent research that is one of the projects that I've been developing with these colleagues in Sao Paulo University. Probably you know Pankaj Kushwaha. He's also collaborating here in this project with our former supervisor, Elisabeth de Gobello Dalpino, and also with Maria Victoria del Valle, and Rafael Alves Batista. We've been, well, previously discussed different aspects of this project, so I will show some results in this multi-messenger modeling of blazar jets. Particularly, as you mentioned, we are using data to, let's say, produce a phenomenological model that can give some insight about the location of the blazar emission that so far is not well constrained, and also the blazar emission mechanism. So the talk is organized as follows. So first, I will introduce some aspects that could be useful to, let's say, understand the concept that I will show in this presentation, like the radiative process in blazars, and what are the things that are currently not well understood. Let me know, is my voice volume okay, or should I?
It's okay. Yeah,
it's okay. Yeah. Then I will describe what is the background jet model for the flow where the emission takes place, and then, well, I will show how this can be employed to interpret multimessenger data that is, well, specifically so far from the Blazar Texas 0506, that is the only or the most significant association of high energy neutrino with electromagnetic flaring. And, well, finally, I will summarize the principal points of this presentation. Well, by multimessenger emission in this talk, I will refer to simultaneous electromagnetic and neutrino signals that comes from a source, as I mentioned, particularly from blazars. Particle emission in this case is neutrino that is being detected in observatories like IceCube in the Antarctica, and electromagnetic signals can be detected by facilities in several wavelength ranges, from radio, X-rays to gamma rays. So this is what we refer to with multimessenger emission. Another kind of multimessenger emission is when we have electromagnetic signals with gravitational waves. Here we are not talking about that, only neutrinos and electromagnetic radiation. So blazars are extragalactic sources. In the sky map, as is illustrated here, they dominate the very high energy bands. So most of just a few very high energy emitters in the extragalactic universe corresponds to, I think, radio galaxies or GRBs, but most of them are coming from blazars. So these sources typically emit their spectra in a double bump way in the new FNU representation, as you see in this right-hand side diagram. This is the typical shape of blazar emission. First bump in low energies, about around 15 hertz, or let's say 1 electron volts, and the high energy that corresponds to gamma rays, could be GV or TV gamma rays. So this emission of blazar spans from around 15 decades in energy, as we can see in this typical blazar spectrum in this diagram. This emission is believed to be produced in relativistic jets, collimated outflows that has the peculiarity to be directed toward our line of sight. These outflows are believed also to be launched by supermassive black holes. And, well, the emission that is observed is typically interpreted in terms of synchrotron radiation of relativistic electrons. These electrons conform a non-thermal population of particles, and together with the inverse quantum scattering, they can be very useful to explain and interpret blazar measurement. Well, these electrons, or could be electrons or positrons, it is not well established if they have a primary leptonic origin or these electrons have a primary proton or hadronic origin. In the second case, when they have a hadronic origin, these electrons are the result of electromagnetic cascades going on in the source, in the emission source, as well as in the extragalactic propagation. And at the end, they emit through their synchrotron and inverse Compton radiation. But well, as I mentioned, it is not very clear what is the origin, if it is leptonic origin or primary hadronic origin. Due to their powerful properties, blazars has also been considered as the sources of the diffuse cosmic ray background and the diffuse high energy neutrino background. So they have been considered as the sources that can accelerate cosmic ray protons up to ultra high energies, as shown by this model by Fang and Moraz. Surprisingly, there are many things or many aspects or basic aspects of blazar emission that are not well understood. For instance, we don't know exactly where blazar emission takes place along the jet propagation axis. It is believed that jets are born magnetically dominated. They are launched by magnetic fields. And at the beginning, close to the supermassive black hole, the jet is point flux dominated. As the jet propagation axis progresses further away from the black hole, this magnetic flux is dissipated to accelerate the bulk motion. The mechanism of this bulk motion acceleration is not for the jet bulk flow, is not jet established also. And actually, we don't know exactly in which region of the jet the blazar emission is produced. So the uncertainty can go from sub-parsec scales to parsec scales. So this is one of the questions that we will be discussing here in this, this presentation. And well, another aspect is that according to the region along the jet propagation axis, the jet encounters different external radiation fields that could affect also significantly the blazar emission. One example of this is that close to the black hole, there are at subparsec scales, we can find the so-called broadline region clouds that scatter radiation from the accretion disk. This is a scenario. And also this radiation field can definitely affect the blazar emission, as we will see later. And also there is another farther away, a torus, a dusty torus, let's say material that is scattering this radiation, especially in the infrared bands. So this is an aspect that is not very clear about blazars. Another question is, as I mentioned before, what is the origin of the radiation? If this is originated from acceleration of electrons, as we see here in the diagrams below. So electrons can emit synchrotron radiation, primary electrons, that can be upscattered due to inverse Compton process. And also they can be annihilated. So a combination of these processes can lead to the typical blazar emission. But also the radiation from these electrons could be originated from protons. Protons accelerated in the blazar zone can undergo electromagnetic cascades. Well, one very applied mechanism is the photohadronic mechanism that produces charge and neutral pions. And these charge and neutral pions cascade down to produce neutrino and electron-positron pairs. And ultimately, what we will see is the radiation from these electron-positron pairs that will undergo again absorption, and then they will produce another generation of electron-positron pairs. Well, this mechanism can also produce direct gamma rays. However, typically they will be very energetic, that they will not be seen by us because of a gamma ray attenuation. And also the direct production of electron positrons is usually assumed to be to occur due to the Bethe-Heitler process. That this is when protons collide with low energy target photons, and then they directly produce electron positrons in the source. Also, the proton synchrotron component, due to this population of high energy protons, in the case that the hadronic scenario applies, can be also significant to model the blazar emission. So, in summary, both models can fit observed blazars, and because of this, it is not clear what is the mechanism. Even if we have a measurement of neutrinos from a particular source, we will see later, it could be the case that the electromagnetic component of this spectrum is just dominated by leptonic origin. So we still have uncertainty on the, let's say, particle origin from blazar emission. And another thing that we also don't know is what is the particle acceleration mechanism leading to this relativistic population of particles that produce the blazar emission. Two of the most considered mechanisms are Fermi acceleration in shock waves and Fermi acceleration in magnetic reconnection in blazar jets. Acceleration in shocks occurs when particles bounce among the hydrodynamical discontinuity produced in the blazar jets, and they gain energy in this process. So this can be described in many references like the ones that I show here by a Fermi process. And then, well, the scenario behind this emission is that shock waves can be produced when faster materials in the jet flow catches slower material. This could be a possibility. And then this produces discontinuity. And well, if the magnetosonic Mach number is suitable for this acceleration, well, this would be a site for shock acceleration. However, if the region is magnetically dominated, this Mach number is very high, and perhaps shock acceleration may not apply. In this case, what is considered is a magnetic reconnection mechanism, and this mechanism occurs when magnetic fluxes of opposite polarity approaches each other and annihilates. So in this time we have a magnetic discontinuity, and again it can be shown that particles can undergo Fermi acceleration or an energy gain in these magnetic discontinuities. So as we see here, this has been studied numerically and theoretically. And magnetic reconnection could occur in blazar jets due to kink stability. This intuitively could happen when a magnetically dominated jet with poloidal magnetic field configuration is precessing. And during this precession, this instability could occur, and then magnetic reconnection leads to flaring emission, also tearing instabilities. And also it could be that, as we will describe later, that a stripe configuration along the jet propagation axis could lead to magnetic reconnection and high energy emission in the jet. So in this talk, we will focus on the possibility and define the conditions under which magnetic reconnection could lead to multimessenger emission. Well, as I mentioned before, this process has been tested with magneto-hydrodynamical simulation in the relativistic regime, as I am showing here in the left-hand side from a work from Kadowaki et al. In the group of Sao Paulo University. where they localize the magnetic reconnection regions with a searching algorithm for these reconnection events, and then they study or they track the acceleration of particles with this approximation of test particle simulation. So with this approach, they can see that particles can attain energies enough to explain, for instance, multimessenger, the multimessenger event of Texas 0506 2017 flare that requires of the order of 10 of the power of 15 electron volts for cosmic ray protons. So this is a very promising mechanism. Also, magnetic reconnection can explain fast variability observed in blazars. This particularly is a feature that shock mechanism struggles to explain, or is very difficult to be explained by shock acceleration. And then, well, as I mentioned, our question here, our principal question in this talk is to see under which conditions we can explain multimessenger emission, particularly this one reported by the ICQ collaboration together with other collaborations in 2017. Our approach will be analytically or semi-analytically. In this case, we consider a jet reconnection model where magnetic reconnection takes place along the jet propagation axis. But this is the process that mainly accelerates the jet bulk flow. As I mentioned before, it is believed that jets are born magnetically dominated. So we will here assume the hypothesis that the jets are producing stripes of magnetic field configurations of opposite polarities. In this configuration, a model developed by Giannius and Ustensky 2019, and also Zhang and Giannius, the jet is dissipating the magnetic energy into kinetic energy. So this transition from magnetically dominated flow to kinetically dominated flow is modeled here in a semi-analytical way or analytical way. And well, this model gives how is evolving the magnetic field and the dissipation power of along the jet propagation axis, as well as the jet bulk Lorentz factor. So here, well, this model, of course, depends on several input parameters, such as the black hole mass, such as the terminal bulk flow of the jet, and also the length of the stripes. So we can obtain, based on the model developed by Giannius and Ustensky, a family of curves. So it is also not very clear which curve to adopt. But what we will do here is to constrain the parametric space of this jet reconnection model with the data of the neutrino 2017 neutrino flare from the Texas 0506 Blazar, and then we will use this to investigate which is the most likely region where.
Juan.
Yes.
Yeah, I'm sorry, I might have missed. But what are these two colors? One is a blue.
Oh, sorry. You are. So here, what are okay? The curves, right? Well, the blue curve. Well, I did not explain this before, but here one of the input parameters of this model is the length of the stripes, here represented in this cartoon, and this enters in, well, I am not putting here the full set of equations, but I am putting here, I think, the most relevant equations. So this minimum length for these stripes it is not very certain. It could be from 100 gravitational radius or 1000 gravitational radius. So in these two extremes, it could be in between. So these two extreme configurations, here I represented the one with 1000 gravitational radii are represented with the gray color, and the one corresponding to 100 gravitational radii for the length of the stripes are represented with the blue color. So any other configuration will lie in between the curves. So I don't know if this is what was your question about.
Yeah, it was all about it. But what this L min physically represent? I mean, if you change L min, then what happens? So
Well,
it's B squared by 4 pi is the pressure, right? Magnetic pressure. And what is on the right hand side?
No. These
No. Go back.
Yes.
Yeah. So B squared by 4 pi. B tilde is what in the co-moving frame? Magnetic field.
Yes. Yeah, exactly. Okay. Yes.
Okay. So
this is
so that's the magnetic pressure, right? In the
well,
co-moving frame.
This is the magnetic pressure, let's say with this we can obtain the magnetic field in the co-moving frame based on the properties, for instance, like a jet power in the observer frame.
Okay. All right. So what is the? I mean, you are equating two quantities, right? So why are you doing that? I mean, from where are you getting this?
Sorry. So you're asking what is the interpretation of this L min?
Yeah, no. You have equated B squared by 4 pi with something, right? Epsilon might be.
Oh yes. Okay. This comes. Let me try to explain. If you want to obtain the magnetic internal energy, you have that let's say the total magnetic power, if you are in the observer frame, let's say in the black hole frame, you see that the magnetic power of the jet is gamma square, approximately gamma square, where gamma is the bulk Lorentz factor, by C by the cylinder radius of this jet to the square, right? Multiplied by the magnetic internal energy. But the magnetic internal energy is the B square over 2 pi in the frame of the jet.
Right.
So the thing is that we are equating this to the magnetic power. And well, this is a very important point. This magnetic power, let's say that the magnetic power plus the kinetic power equals the jet total power. So this quantity is conserved. So the things that you transfer from magnetic power to kinetic power in order to conserve the total jet power. But you can, from here, you can obtain the magnetic power in terms of the total jet power, and also in terms of the kinetic power. So the kinetic power, we will see that is associated to this bulk Lorentz factor. Well, from this, let's say, this is what we equate. I don't know if this is more clear than before.
Not much, but anyway, we can discuss later on.
I can write down this, but I don't know if it is. Well, imagine that magnetic power plus kinetic power is the total jet power. This total jet power is LJ, right?
That's fine.
So from here you obtain you solve for the magnetic power.
So is your simulation magnetodynamics or it's magnetohydrodynamics? If it is magnetohydrodynamics, then also the the internal energy, pressure, the gas pressure, and all these things should also be there.
Oh yes. Well, the thing is that in this case, this is also considered in this model, in this equation. As a matter of fact, this is an analytical model. This is not a simulation. But well, also the gas pressure should be considered. The thing is that this is a transition where the magnetic energy is transferred to kinetic energy.
Okay, okay. All right.
And this is modeled by this equation. Well, more details can be seen in the derivation here in this paper, Janusz and Mustensky.
Okay.
We can, we can check it later on there.
Yeah, I'll check it later. Yeah.
Okay.
Yeah, please go ahead.
Okay. And well, as I was commented to you, it is not very clear what is the correct configuration that we should employ, but we will use data phenomenological in this phenomenological approach to constrain this jet reconnection model, like the terminal bulk Lorentz factor, and also this element that you were previously asking for. And well, some of the quantities or physical quantities that is produced by this model are, as I mentioned, the jet Lorentz factor along the jet propagation axis, the ratio of magnetic power above kinetic power, that it is associated to the magnetization of the jet along the jet propagation axis, the magnetic field in the jet common frame, how this is its behavior, and also the dissipation power that is associated to the transition from magnetic to kinetic energy. To constrain these quantities, we will employ a single zone leptohadronic model in order to reproduce the spectra of the spectrum of the 2017 flare, neutrino flare from the source Texas 0506. And well, even in this modeling, there are several possible scenarios. Well, what we've seen in the previous works by Cerruti, Gao, and Kivani is that leptohadronic models works better, or at least produce the highest possible neutrino fluxes, where this leptohadronic or mixed model are those that are produced in a single zone, but also that the low energy and high energy components of the blazar bombs are dominated by synchrotron and synchrotron self-compton. So the hadronic component here will produce the neutrino flux, and also will contribute subdominantly to the electromagnetic components. In this case, for instance, will be limited by the data at X-rays and gamma rays in order to, let's say, we have to respect the data to put a maximum, let's say, limit for the power or for the hadronic emission, and this automatically will limit the neutrino flux. In order to give some estimates of what set of parameters to adopt, as I mentioned, I will consider the low energy peak of this event that is here in approximately optical, and the high energy. We know that they are in the synchrotron self-compton scenario. They are related, the observed emission, by let's say the energy or the square Lorentz factor of the electrons. So the peak of inverse Compton radiation is related, multiplied by the square of the peak of synchrotron radiation by the square of Lorentz factor. And also the fact, with this we can estimate how the magnetic fields and the jet Lorentz factor would be related in terms of these observed quantities, which is here plotted in the red with the red line. Okay, the red curve. The other curves correspond to in this magnetic field bulk Lorentz factor diagram corresponds to the solutions that I shown before for the jet model. So the intersection of these curves could give you an idea what are the typical parameters that could satisfy this SED data in the synchrotron self-compton scenario. So we can see here that solutions are then expected to have a magnetic field in the comoving frame from 10 power minus 1 to 5 Gauss, and bulk Lorentz factors around, let's say, tens, from 10 to 20 or so. In this case, the solutions can be, before modeling, can be constrained that will lie in approximately 10 parsecs, below approximately at 5 to 10 parsecs. So then we will, if we provide the location in the jet propagation axis, then we obtain the solutions. Particularly, as I was commenting before, if we situate in a magnetically dominated region, then it's very likely that these particles will be accelerated by magnetic reconnection, because over there shock acceleration will not operate. So here we will consider this particular solution in the gray color, where, as I was commenting to you, it corresponds to the maximum length of the stripes, that this corresponds to 1,000 gravitational radii. So adopting this solution for the jet background flow, then we will build our emission model based on a single zone leptohadronic model, as I previously mentioned, where we assume that primary electrons are already accelerated in this one zone region, and also cosmic ray protons. Primary electrons will be responsible for synchrotron emission and from synchrotron self-compton, and primary protons will be responsible for the emission of neutrino, and the cascading from neutral pion and charged pion. We also will consider a Bethe-Heitler cascade in this calculation, and proton synchrotrons. And this, the total emission.
Yeah, Juan, can I ask one question?
Yes.
Like, this location of the emission along the jet. So you showed that there is the dissipation, and in the previous slide, the vertical, so more or less, it seems like the dissipation is at the border, and it's preferring the magnetic reconnection rather than the kinetic dissipation, after the crossover. So are you discarding the kinetic dissipation in this case?
No, actually, no, we are not discarding that. The thing is that we constrain this shade region based on this intersection. And actually, this depends due to the fact that we are assuming that both the low energy and high energy peaks are, let's say, described by the synchrotron self-compton scenario. If we change this possibility, for instance, that we assume that the high energy bump of this blazar emission is produced by proton synchrotrons, for instance, this assumption is not any more valid.
Okay.
But
so this is for a particular assumption it works. Okay.
Yeah, exactly. This particular assumption that synchrotron self-compton is producing most of the electromagnetic emission, or at least they dominate the low energy and high energy bumps. Okay. So this constrains this region for the model. These chords, the green and blue chords, correspond to the model. That's why I can localize these regions here corresponding to this intersection. Okay. The thing is that, and why I am assuming this synchrotron self-compton scenario. This is just because in previous works that are not modeling the jet background, but they are just parameterizing the blob emission, they find that this is a scenario where synchrotron self-compton producing most of the electromagnetic radiation and the hadronic contribution only models the neutrino flare, the neutrino flux. They are like the models that works better than other models. That's why I am assuming this scenario. But well, as I don't know if this answers your question.
Yeah, thanks.
Well, those are the components of our radiative model, and here we have some result curves. As I mentioned, we are sweeping the the location of this single zone electrohadronic model from 5 to 16 parsecs. And we, well, as you see, the properties of the background jet flow is changing with this with this distance. And then we obtain different configuration for the blob emission. And then we arrange the parameters of the electron population in order to appropriately fit the data. As you can see here, we have two very visible figures. Is that closer to, or for lower location for the Blazar emission, in the case of 5 parsecs in these solutions, we have the maximum flux for neutrino emission, and we do not completely satisfy the gamma ray data, especially the ones corresponding to the very high energy regime. As the location of the emission zone is located farther away, namely to 10 parsecs, for instance, we start recovering or satisfying the very high energy data. But the result or the consequence is that the neutrino flux is diminished, right? So this is constrained also by the proton power that is assumed for the population, that is constrained by the model with the dissipation power. So the dissipation power, as you see before, is also a function of the location in the jet propagation axis. And also here I am reporting the magnetization. Yes?
There's one more clarification. Are these data simultaneous or quasi-simultaneous, these black ones?
Well, the black data is quasi-simultaneous. I will show the light curve of this data. Okay. I think in the next slide.
Okay.
For instance, perhaps this answers your question. So those are data from optical up to very high energies. Here in the bottom, we have light curves in optical, and we have here X-rays, and we have gamma rays as reported in these papers published by the ICQ and other collaborations from this 2017 neutrino flare. In this vertical red dashed line, we have the neutrino event. And then, well, the SED was built considering all this data. But, well, what it is a subject of interpretation or an investigation from our side is that whether this modeling is correct, in the sense that we have that when we have the maximum neutrino flux, we do not predict very high energy gamma rays. However, as let's say somehow the emission zone evolves going farther away from the black hole, we have the emission, the neutrino flux drops and very high energy emission rises. Perhaps this could be interpreted in terms where the neutrino event is produced when the GB gamma rays are in upper state, and then as the very high energy component rises, then, well, there is no neutrino anymore in this. Well, this is a subject of investigation and interpretation. But so far, this is what we obtain if we consider this jet reconnection background model. I don't know if this is related to your question.
If I may ask, so have you considered the radio data to fit the model, or you don't include the radio data?
Oh, okay. This radio data is not considered because I can show here. I think these do not correspond to a flaring state. This radio data. This is also the same data. I took the data from this from the original paper, as I'm shown here. So I am not considered the radio data because it's not flaring, and is assumed not only here but in many papers that this comes from a large scale jet region. Perhaps this comes from the large scale lobes of the
okay, so it's not maybe due to core, but maybe lobes, extended KPC scale lobes or something.
Sorry, I
mean it's not from the core of the jet, or it's coming from the lobe of the jet.
Yes, this could be a possibility. So
Okay.
the thing is that it is taking into account that in the blazar zone, the condition would be that we do not overcome this radio data. So this could be somehow the condition that where the radio data is applied to this model. But as you see, well, there is it is not very well constrained where the lower energy for the electrons should be set, because, well, you know that this corresponds to the lower limit for the electron population. So just the condition is to not overcome the radio data, and this is using the fact that this data is not flaring, it's not in flare state where the neutrino event occurred. So, well, this is, I don't know if this answered your question.
Yeah. But how do you know that this is not in flaring state? From the light curve, it
could
from the
be
light
from
curve it was looking, or it was not flaring. Okay, anyway.
Yeah.
Yeah, it's variable, much variable, but of course not flaring.
It's also discussed in this paper.
Uh-huh.
I don't remember exactly which part of the paper, but it's also discussed. But it could be also interesting, by the way, to implement the large-scale jet, let's say, emission, because also this jet reconnection model that I am investigating here also predicts the emission for the large-scale jet. So it would be interesting to introduce this other component, and whether or not this is consistent with radio emission with the rest of the. Let's say we will have here a background emission from in radio from the large scale jet, and then over this we will have the flaring state.
Okay.
Well, this is another possibility. So
yeah,
I think very interesting possibility. And well, finally, well, I also would like to show to you from the same jet reconnection model, we can consider external radiation fields. We know that blazars can have in the surroundings of the supermassive black hole radiation fields produced by a broadline region or a putative broadline region and a dusty torus. So they upscatter or they reprocess the radiation from the disk, permeating some regions of the jet with target photons that could affect the blazar emission. Considering these photons at the broadline region and at the location of the dusty torus, we build a very simple model where we consider the dissipation power at those locations and also at the peak of the dissipation of the jet to derive the multi-wavelength emission and multi-wavelength and neutrino emission. So in this scenario, when both external radiation fields are applied, we have that the high energy pump of the blazar emission is mostly dominated in the dusty torus, and the low energy emission of the blazar is dominated by the emission in the broadline region. And well, we have also thermal components, and we have that here that the neutrino emission peaks at 2018 electron volts. So this is perhaps not very appropriate to model an event like Texas 0506, where the neutrino event lies at 10 to power 15 electron volts. However, the difference of this, let's say, model with the previous one that I showed to you is that here we are assuming or balancing the maximum energy of cosmic ray protons with the radiative losses. In the previous modeling, for instance, in these SED profiles, we impose that the maximum energy of cosmic ray protons are 10 power 15 in the observed frame. So this imposition is in order to, let's say, not obtain a neutrino flux outside the measurement. in this measured energy range. And well, that's why this model is based on observations of this is the phenomenological model. But if we consider the balance between acceleration rate and relative losses, the predicted peak is at 10 power 18, for instance, in this case. And well, also we can correlate this with the accretion state of the central engine. If we consider, for instance, a given black hole mass for the central engine and for different mass accretion rates, well, what we are trying to derive here is what is the behavior of the blazar emission, and whether or not this can reproduce the so-called blazar sequence, that this is an apparent trend observed from the blazars of all the blazars measured in the universe. This is also very debatable whether or not this blazar sequence exists in reality. But for instance, here we employ this magnetic reconnection jet model, parameterizing in this way the properties of the properties of the jet. And well, we derived or try to model the blazar sequence where the line emission appears as we increase the accretion rate. And also we obtain this shifted, the shifting of the bumps to the left as the blazar power or the accretion rate increases. And also the consequence of this modeling is what is the corresponding neutrino flux? What is the neutrino counterpart? Well, this is ongoing research, and we believe that this could be very helpful to interpret in these terms the high energy neutrino background detected by for instance, by IceCube observatory. And well, I don't know if, yes, I will finish here my talk. I am just summarizing here that, well, what I have presented to you is a leptohadronic blazar emission model, where we, assuming that this emission is produced in the magnetically dominated region of the flow, assuming a background flow model, this could be very likely to be produced by magnetic reconnection. And for this, we employ the striped model developed by Janius and Ustensky, that it is modeling the flow of the jet as it is going from magnetically to kinetically dominated regime. We constrained this emission model by fitting the neutrino and electromagnetic data from the 2017 event from the Blazar Texas 0506. Doing this exercise, we obtained that the blazar emission is produced at approximately 5 to 10 parsecs. The neutrino emission, the most prominent neutrino flux is produced in the magnetically dominated region from the models presented here. And well, considering external fields like the broadline region and those produced by the broadline region and the dusty torus, we can obtain different blazar models that could be useful to interpret the high energy neutrino background. So thank you very much for your attention.
Okay, so thank you, Juan, for the interactive and nice talk. And let us check if there are any questions from the audience. So if anyone has any question, please unmute yourself and you can ask the question to Juan. Yeah, directly.
Yes.
Juan, nice talk. So I am, so can you go back to 3-4 slides? I mean, go back 3-4 slides. Yeah, so here, I mean, where you are showing the ACD for given black hole mass and you calculated the Eddington ratio.
Oh, yes. The black hole mass assumed here is 10 power 9 solar masses.
So my question is, how sensitive is this plot on the black hole mass?
Oh, yes. Well, this is even sensitive to the black hole mass, but also to, because, you know, the length of the stripes, that is also a parameter here.
Mm-hmm.
That this is a question that I don't know if you asked before or another colleague.
Yeah, another colleague.
Okay,
But
this
I
is related to
got
the.
it. I got that point. So yeah, you can go.
This is related to the
Okay.
black hole mass, the length of the stripe. So these different solutions here are generated as a function of the minimum length of the stripes. So the length of the stripe is proportional to the gravitational radius.
Oh.
So this is where it is interesting. These solutions are derived from a black hole of 10 power 9. So why we choose this black hole? Because this is also related to how much power we will assume for the jet in terms of the Eddington power that is also enters here in the black hole mass by jet. So, and then the power of this, the total power for the jet is also assumed here for obtaining the magnetic field configuration and also the dissipation power and some other properties over there. So how sensitive, I believe, it is sensitive in terms mostly on the total jet that is assumed. And also, actually, for instance, for these models, we assume that the jet is holding 80 times the Eddington luminosity. In this sense, this is super Eddington jet.
Okay.
For this case, this is this is let's say very strong assumption, but I would like to point out that typically for hadronic models, super Eddington luminosities for jet must be assumed, not only for the modeling that I am presenting here, but also for the modeling, for instance, that I am quoting in this, for instance, these previous works. Also, well, the jet power should be significantly super Eddington.
Okay, thanks.
So, I mean, again, that I'm Indranil, by the way. Okay, so I'm asking again. So, if it is, you know, significantly more than Eddington power, then from where it deriving that extra energy supply? Is it? I mean, while computing, is it I mean, is the jet getting it from the magnetic energy dissipated or something else?
Well, the things that this is why this is super Eddington or not is not included in the model because
No,
the
but
model.
some physical argument. That's what I'm looking at.
Well, this is a process in the launching region. Here we are assuming that the total jet power is already given. So here we are not discussing.
I understand that, but if the jet has to come from the accretion matter, so 80 times 80 times the Eddington limit is way too high.
Yes, it is.
Generally speaking, that can happen in transient events, but not so in say in blazars, which are, you know, which are not transient, right? It is.
Yeah, well, that's very right. That's also a discussion that are in several papers where, well, in that case, hadronic model doesn't work if you assume luminosities for the jet below the Eddington luminosity. So you have to assume, at least for these only internal target photons. However, if you consider external target photons, you don't need that much power to reproduce observation. But this is an issue that is also faced by previous models. This, I agree with you, this is a very energetic requirement.
So from other arguments or other estimations, what would you say is the baryon loading for these jets? Because you are taking Lorentz factors of 10, 20, 30, right?
30 for the terminal.
Sorry?
This is for the terminal bulk Lorentz factor.
Yeah,
but in the
I understand. What I'm trying to say is, I mean, if you favor, for example, an hadronic model, and your the luminosity is the jet luminosity is way above the Eddington luminosity.
Mhm.
So then what would you, I mean, say about its baryon loading of the jet?
Well, this is not, this is a good question. I have not computed it here,
Okay.
but I think this could be also another criteria to constrain the model or to rule out some configuration. Actually, this is not calculated or contemplated for this model. So the answer, the short answer is I don't know for what is the baryon loading for this that corresponds to this model. But actually, this, thank you very much. This is a very good point that I should consider in order to see whether or not the models that I am obtaining or deriving here are correct.
Yeah, it's okay. It's fine. A nice talk, by the way. It's very.
Thank you, thank you.
So Juan, I have one question. Like, when you say this neutrino flare, so what does that mean? Does that mean there are more than one neutrino coming from this direction, or how do you interpret a neutrino flare in terms of number of neutrino events?
Well, in this case, there was only one neutrino event, but the thing is that well, I call it flare because it was associated to flaring in the electromagnetic bands.
Okay, that way. Okay.
So there was a detection of a single neutrino, and then this, as you see here with the time,
Yes.
there was associated also flaring in the other bands. So
And you consider both, like PP interaction and P gamma both now?
No, only P gamma. PP is not, proton is not relevant here because you need for proton you need a very high gas density.
Yeah, the density torus can provide the gas density, I guess.
Yes, actually that could be a possibility. The thing is that here we are considering only emission within the jet here. But actually what you say is also a possibility that we also started to explore, but well, it's a little bit more elaborated. Cosmic rays that escape from the jet and goes to the dusty torus. Actually, that would be a very nice
diffusion,
possibility.
maybe transport of cosmic rays, maybe diffusion coefficient can be constant that way.
Yes, but the thing is that you have to take into account that they should not be, let's say, the flare of cosmic ray acceleration should have a delay until this diffusion reach the dusty torus and then interact. So,
so you need some observational signature at least to do that. Yeah.
Yes, but the things that something that could be similar to what you are proposing is perhaps interactions with the broadline region clouds. Well, assuming that there are broadline region clouds over there. And then what would be the interaction of one of these clouds that can have a higher gas density than the jet material? And then the cosmic ray interacting with this relatively high density gas could have a relevant proton-proton emission. And well, what
so one more question, actually, like, about this black hole mass in this object. Do you have some other, like, limitation or constraint by the observation, or you put it by hand?
Well, the thing, I put it following previous models that assume this black hole mass 10 power 9, and actually I've seen other models that assume 5 by 10 power 9 solar masses from this black hole. But actually I've seen that there are
because that can control the Eddington luminosity, I guess. Is that correct?
Yes.
So
yes.
one can play with that.
We can play with it, but the thing is that this is also constrained because, as I mentioned also with the other colleague, to the power requirement for the jet. So it should not be very low because then you will be assuming very high super Eddington luminosity. So if you increase the mass, the central engine mass, then you will not have this tension. For instance, as you assume higher black hole mass, then you will not require super Eddington or that much super Eddington luminosity.
It can lower the requirement. Yes.
But actually, there should be constraints, independent constraints for the central black hole of this from this source. So perhaps from based on other observations. And actually, well, I don't know exactly what is the constraint about this black hole mass, but this is a thing that I must also investigate in order to further constrain these models.
So if any other question there from the student, somebody? Okay, if not, then thank you, Juan, for the nice talk. And yeah, we might
thank you for your invitation.
next time. Yeah.
Thanks for the invitation, and see you.
I mean, Juan, you should sometime visit here.
There are okay, that would be very nice. Would be very nice.
Yeah, Indranil also works in relativistic outflows, so you guys can interact more about these modeling.
Okay, thank you very much. And thank you also for your questions, because this was a very interesting feedback, especially the question that all your questions, guys. So thank you very much. This will contribute a lot to the reporting of this work.
Okay. Thank you everyone for joining us. So we will meet next time on the seminar. So bye-bye.
Ciao. Bye.
Ciao.